Hola, compadres. Welcome back to another video for the Mathnasium. Let's do some more learning on circuits, if you don't mind. Yeah, this is going to be fun. I'm real excited. Let's go ahead and get started. So, anytime you buy an electronic device, an electrical engineer created a circuit like this. There's a common language that engineers use in circuitry, and all symbols kind of represent there's symbols for different things. When you see a little gate like this represents a switch, this is a light bulb, so on and so forth, battery. We're not going to do a whole ton of this. If you want to do, we'll kind of talk about some of the general signs and symbols, and if you have questions, if you want to try and draw a circuit on paper, this is the way that a lot of people will do it. So feel free to learn these, but I'm not going to require you to do them on your homework. Mr. Million in his automotive class will do these quite often. So circuit drawings, like if you buy a refrigerator, you can look at the circuit drawing for the wiring in the refrigerator. That used to be, it's on the back of my fridge, my older fridge in here. So yeah, all electronic devices are going to have some sort of a wiring diagram, and even high-powered stuff is going to as well. So this is what the circuit drawing for just a basic light bulb circuit is going to be with a switch. Okay, let's keep cruising. All right, so batteries. What you don't need to draw the battery if you don't want. Just remember red, positive, cathode. Okay. Conventional current has electrons traveling from the cathode, the positive or the red side, out through the equipment and then back to the anode, which is the negative or the black side. So, or this is often called ground. So black represents ground, which is negative, so on and so forth. In fact, let's go ahead and write that on here so no one's confused. Yeah, black, ground, perfect. So yeah, ground, sometimes abbreviated GND. All of our houses have grounding rods. Literally, that is a escape for electrons into the ground, the end of the circuit. So pretty cool gig. Some houses have multiple as well. So all I need you to know about batteries or about our power sources is we always start with the red. You can get in the habit of just looking at a power source and just clicking, but I'll tell you that you got to be really careful, especially with the circuit program we're using today, because on certain sources they switch the order of them to make sure you're paying attention. So you start at the red. Conventional current goes from positive to negative. Okay, and that's what we're going to be using. I like to do a quick refresher of your metric prefixes that are important. Today, we are primarily going to be working with resistance, and with resistors, you use mega and kilo to talk about the different sizes. And you'll recognize these like terabytes, gigabytes, megabytes, kilobytes. So a terabyte hard drive, we think of that as 1,000 gigabytes. That's what it is. It's 1,000 gigabytes, right? But it's really a trillion. It depends on what you're referencing it to. It's 1,000 gigabytes, but if you're thinking about it in bytes, it's actually a trillion bytes, and it would be a billion kilobytes and a million megabytes. Cool. Okay, so mega and kilo are the ones that we're dealing with resistance, and this chart you might come in handy later down the road. Okay, so if you have, what is that, 5 million ohms. 5 million ohms is going this direction. I can't remember which direction I did in the other slides, but if you're going, these are bigger things, right? Going this direction, you're going to divide by 1,000 to get the number. So this is 5,000. 5 million divided by 1,000 is 5,000 kilo ohms. Okay, and divide by 1,000 again, which is 5 mega ohms, with a capital M. Okay, 73 kilo ohms. Okay, dividing by 1,000, going this direction, I move that decimal place over 1, 2, 3, is 0.073 mega ohms. Okay, and going this direction times by 1,000 73,000 ohms. Oh, we got another one over here. 0.6 mega ohms is timesing by 1,000, 600 kilo ohms. Timesing by 1,000 again is 600,000 ohms. Okay, you try this one on your own. Try 600 ohms on your own. If you get it, great. If not, maybe try a couple more with somebody else watching. Yeah, so this is our ohms. You can pause it now if you want to try it on your own. And then kilo ohms, we're going this direction, divide by 1,000, 0.6 kilo ohms. Oh boy. Yeah. 0.6 kilo ohms, which is divide by 1,000 again, move it over 1, 2, 3, 0.0006 mega ohms. Okay, my question to you is in a circuit with a resistor with these 4 different resistances, which one is going to have the highest current? Which one is going to have the highest current? Okay. Well, the highest current is going to go to the circuit that has the lowest resistance. Remember, Ohm's law is V equals IR. So when this value is really low, so we have like 120 volts, you divide by a really small number, then this will be bigger. If you divide by a big number for the resistance, then your current will be smaller. So it's the smallest resistance that makes a higher current. Interesting. Moving on. Okay, let's learn about resistors. Now we're going to do some new stuff. Review's over. Let's keep cruising. So resistors, we protect our equipment with resistors. That's the whole point, and I've gone over that. So there are different kinds of resistors, some with 5 stripes, some with 4. All the ones that you're going to be dealing with today are 4-stripe resistors. And yeah, so the big thing here with resistors, when you're constructing a circuit, it doesn't actually matter which direction goes where. The resistor is going to provide, it's made out of a semiconductor, I believe, and it's going to provide a certain amount of resistance no matter which direction that you face it. Remember, we want to use the resistance as a tool. That's something that we can control to help protect the components that are in a circuit. Okay, moving on. Yeah. Okay, so this is how they're read. When you have 4 stripes on a resistor, it's really the first 3 that matter. I mean, the last one matters, but we'll go into that in just a sec. The first 3 is really all that you're going to have to worry about on your assignment. I'm going to give you 4 stripes because that's how they're presented. But it's really the first 3 that matter. So let's go through. If we are reading this resistor, you always put the silver or gold stripe on the right. Okay, so silver or gold on the right, and then you read the first 3. This one reads black is 0. The second band is red, which is a 2. And the third band is what's called your multiplier. So these are digits, 0, 2, and then this is your multiplier. So you take the number 2 and you're multiplying by 10 to the 5th. Well, 10 to the 5th is a 1 with 5 zeros. Anytime you multiply by 10, you add a 0. Anytime you multiply by 100, which is 10 to the 2nd, you add 2 zeros. So it's just really kind of the number of zeros you're adding with some exceptions. Be careful down here. This moves in the opposite direction. But let's do this right now. So this would be 0, 2, and then we add, it's times 10 to the 5th, which means we add 1, 2, 3, 4, 5 zeros. So that is 200,000 ohms. 200,000 ohms. We just did the conversion, is 200 kilo ohms. Or it is also 0.2 mega ohms. So which one makes the most sense? I think this one's probably the easiest to write. That one is also easy to write. So either kilo ohms or mega ohms is the units that make sense. So what's the last stripe? What's the fourth band on our resistor? Remember, that one's usually gold or silver. Just make sure you read your resistor kit, whichever ones you're using if you were to buy one. It'll tell you how to read it. This is what's called the tolerance. So the tolerance is like how accurate our resistor is. We're humans that are making these things, and it's depending, you know, whenever you're engineering something, there's always the time you put into it and then the quality that the object is. Whenever you're building something, the faster you build something, typically the worse it is, and it's not going to last as long, right? Well, with resistors, it's kind of the same thing. There's a trade-off for time and accuracy, or difficulty and accuracy. Ones that are easier to make are probably not as accurate, but you may not need a resistor to be super accurate depending on the device that you're using. If you're just using an LED, it doesn't really matter how accurate you are. So the silver is not as accurate. So the resistance can vary by 10%. Gold can vary by 5, and if it's a red stripe at the end, it can vary by 2%. Okay, so really, so this is super accurate. This is not super accurate. Like an LED, big deal. LED burns up because the resistor isn't very accurate. LED doesn't cost anything. It's not a problem. But if you're talking like a nuclear reactor, well, that's kind of dangerous. So you may want to make sure all of the resistances and for something that is very high danger or high level of risk associated with it, or expensive, you want those things to be very, very protected. So you use high quality resistors for those. Let's do some practice. Yeah, 0, black, brown, red. I think I got it. White's 9. Okay. Oh, shoot. Let's do let me change the order here. How did I screw that up? All right, let's move that down. Let's do some practice with the resistors. All right, red, black, green, yellow. Go back to our sheet. Red, 2, black, 0, green, 5. And, oh, sorry, red, black, green, and this is gold. This is our last stripe. So red is 2, black is 0, green is 5. That means this is 20 times 10 to the 5th is what this means, which is a 1 with 5 zeros. So we take 20, and that just means we add 5 zeros to it. 1, 2, 3, 4, 5. That is 2 million ohms, which is equal to 2,000 kilo ohms divided by 1,000, which is equal to 2 mega ohms. The unit that makes the most sense here is probably mega ohms. That's super easy to write. Much easier to write 2 mega ohms than it is 2 million ohms. Next one. Orange, yellow, blue, and then gold at the end. Orange, yellow, blue. 3, 4, 6. Let's go back. This is 3, 4, 6. So that's 34 with 1, 2, 3, 4, 5, 6 zeros. So it's 34 million ohms, which is 34 mega ohms, or 34,000 kilo ohms, but mega ohms is easier. Okay, next one. Yeah, this is different. Brown. All right, so this is yellow, which is 4, 3, and brown is 1. Yeah. 4, 3, 1. All right, so that's 4, 3 with 1 0. It's 430 ohms. Okay, so we don't need to transfer this. That is a perfectly acceptable unit to write it that way. You could write it as 0.43 kilo ohms if you wanted to, but this is just fine. And they're both the same. Either is acceptable. I'm going to do one more that's not on here. Let's do green green, black, silver. Let's think about a resistor that is green, green, black, silver. So let's put a little dotted line here. Green is 5, so this would be 5, 5, and remember this is the number of zeros. If we look at the chart, black is 0, so this is 0 zeros. So the answer is just 55 ohms. That's our answer. And if you're wondering about these other ones, let's do another crazy one. How about purple, red, purple, red, and then let's grab one of the other colors like gold. Purple, red, gold, gold. So if you looked at that gold chart there, purple is, well, violet is 7, right? So this is 7, 2, and then it says 10 to the minus 1. Okay, it's the multiplier. It's not necessarily just the number of zeros. So this is 7, 2 times 10 to the minus 1. Well, 10 to the minus 1 is 0.1. So how many ohms is this? 7.2 ohms. Okay, see how that works? That's the other method. Okay, I think we've done enough. Let's move on. So those on your assignment, it's going to be listed in this fashion for if you're those people that are doing it in paper, the take-home assignment. Okay, next vocab we need. A diode. What is a diode in circuitry? It's something in a circuit that only allows electricity to flow one direction. You know, electricity in our walls is alternating current, so it'll only allow electricity to go one direction and not the other. LED, which we commonly hear, stands for light emitting diode. Okay, LED or light emitting diode on the online service that we're going to be using called Tinkercad. They have a side that's flat, and then they have a side that's rounded. This is all the way around, but there's a spot where this little circle is shaved off. And then this is the shorter leg, and this is the longer. I can't remember. We'll have to take a look. Anyways, look at the side that's presented there. But the side that has this missing is the side that is shaved off in our circuitry, okay? That's our negative side, so this should be hooked up to our negative. This should be hooked up to our positive, okay? Here's an example of what it looks like in our circuit drawings. So diodes have an arrow. There are regular diodes that look like this and light emitting diodes that look like that. So they will allow electricity to flow only one direction. If the diode is facing the opposite direction, the circuit will not be complete. Think of it kind of like a racetrack, right? This is like something that's like a wall, right, for the electricity, and it can't get up the wall, but it can go down in this situation. Okay, so that's kind of how a diode works. So why am I teaching you this? Well, if you have a diode backwards, your circuit's not going to work. So don't be racking your brain on the online program if you don't understand what's going on. So make sure you check and you got stuff hooked up. This should be hooked up to negative or black, or the anode. This should be hooked up to positive or red, the cathode. All right, so let's get into Tinkercad. We're going to use an online program called Tinkercad. I'm really excited about it. It looks like this. Tinkercad, you can just sign in with your Google account. You don't need to make an account. You just press sign in with Google. And there are a lot of cool services. It's a product of Autodesk. There are a lot of cool services that go along with this program. You can do like digital 3D drawing. You can also mess around with circuits and do some coding as well. So we're going to go to circuits, and we are going to open up a new circuit. So these are all the circuits that I've created here on this account. You can just press create new circuit if you want to try this. This is a blank circuit that I've already created, so I'm just going to press tinker this. We're going to go in. They have these weird funny names. They're just automatically randomly generated. You don't need to change the name if you don't want to. But yeah, so let's go ahead and get started. So over here you have all these components, and you can kind of sort, and it can get very complicated. The amount that you can do in this program is fantastic what you can do. So let's go ahead and it says use a 4.5 volt battery pack, 1 resistor, and 1 LED. So if I have 4.5 volts and I want my LED to operate at roughly, I think it's 15, I think we want around 15 milliamps for the LED. I think that's right. Oh, I made that number up. Hope it's right. Okay, and we have voltage equals current times resistance. The voltage we have is 4.5 volts. The current that we want is 15 milliamps, which is 0.015 amps. And we get our resistance. So let's go ahead and grab a calculator and figure out what that is. 15 milliamps. Yeah, I think that's right. 5 divided by 0.015. Okay, it says here we want around, if you divide both sides, we want our resistance to be around 300 ohms. Okay, so I'm going to go into my circuit. I'm going to grab an LED. I'm going to grab a battery pack. I'm going to grab a resistor. So let's see here. Search. If you want to rotate an item, you can click here and spin it. I told you the direction of the resistor doesn't actually matter. I'll zoom in so we can really see what's going on. We got a resistor here. We got my LED, and we can kind of spin here as well. So I'm going to grab a battery pack. Battery. There we go. To get 4.5 volts, you can take your normal battery pack. Zoom out a smidge. Take your normal battery pack, and you click on it, and there are options. You can select AA or AAA. Doesn't actually matter because each one is still 1.5 volts. You can select the number of batteries. 1.5 times 3 is 4.5 volts. And you can even name the battery pack if you want it. So here's my resistor. My resistor is reading brown, black, red, which is 1, 0, so 10 times 2, or 10 times 10 to the second, which is 1,000 ohms, or 1 kilo. There we go. So we can use this, and the stripes on this program will follow what we just learned. So we want this to be 300 ohms, so we click the ohm option, and let's see if we can predict what it is. So 300 should be 2 zeros, so it should be 0, 3. 3 I think is yellow or orange. I think it's orange. So it should be orange, black, and then a multiplier of 1, which is brown. 300 ohms. Yeah. All right, so orange, black, and brown. There's our 300 ohm resistor. And then here is our LED. If you click on the LED, you can choose the color that you want. I like working with the red LED personally. Okay, so here's what's cool about this program. You can draw your circuits. Remember, we always start with the positive side. Another question is, which side of the circuit does the resistor go on, the positive side or the negative side? It actually doesn't matter, okay? It doesn't matter which side, because wherever that resistor is, it's a complete circle, right? So electricity, it's going to slow the electricity no matter where the electricity is. and it's gonna all the electrons are bunched up in like almost like a traffic jam moving through. So if you put it on this side, it's gonna go the amperage will be the same as if you put it on that side. Okay. So we start with the positive side. Positive, you can click, and you can actually make these look really pretty. You can have them take these nice, pretty turns. We're going to connect to the positive side of our LED. Okay, and then I'm going to come down here, maybe take a sharp right 90, connect to our resistor there, and we take some 90-degree turns to come down and complete our circuit. Let's go ahead and start the simulation. Hey, look, our LED is on. Look at that. It's beautiful. Okay. So if I were to click on the LED, I wonder if this is going to change. It's hard. You can't really make changes to your circuit once the, you can't make changes to your circuit once or certain changes once you've pressed start simulation up here. But you can, let's see, you can change certain things. I'm not sure if this is one of them, but I think if I change this to a 30 ohm resistor, it says, hey, look, you are currently operating at 63 milliamps on your LED, and that's too high. If I change it to 3, it shows the LED breaking. Okay. So change it to 3, it shows the LED breaking. If you were to just hook up the battery pack straight up to the LED, it would be bad. Now, what if I add too much resistance? What if I change this to 300 kilo ohms? The light is barely on, right? That's 300,000 ohms. The LED is barely on. How about 300 mega ohms? Doesn't even look like the light is on at all. Okay, so you got to make sure you have the correct unit selected over here. We want around 15 milliamps, and that's what we did our math with our Ohm's law to show that. If you change the battery pack and we change this to AA's, won't change anything because they're the same voltage. But if we change this to 2 batteries, you'll notice the light gets a little bit dimmer. That's because we're operating with 3 volts and not 4.5 this time. If I change it to 4 batteries, the light gets even brighter, but it's still operating at a safe zone. But 3 is where we're at. So we use Ohm's law to help protect the equipment that's in our circuit. Okay, so that's just a regular old simple circuit. You have one item, you have a resistor, you have a power source. There's our voltage, our current is the rate at which electricity is flowing, what's controlling kind of how bright the light is, and our resistance is slowing everything down. Let's keep going. Next. Now we're going to incorporate the use of something called the breadboard. So breadboards are in our Arduino kits. I really wish you guys had the chance to do this with actual Arduinos, but I think doing it, this is a great alternative to trying to do it on paper. So we have our breadboard. Basically how it works is it eliminates the use of tons of wires. So it allows you to make connections and order things and keep things organized without having to use a whole lot of wires. So how a breadboard works is you can send electricity to something like this, and you see how those rails are connected all the way up and all the way down. This positive rail is not connected with this rail. It follows the connections that are listed in this picture. So these ones run vertically, these ones run vertically, and these run horizontally. Now these are not connected across the middle. So if you put power to this point, then all of this has got power. If you put power to H1, then that whole row has power. It doesn't matter where you put it, right? So you can run electricity into one port, and it'll run out a different spot. Let's see here. How do we typically use a breadboard? So really what you do is you put power, the positive side of your circuit, connected to there, and you put your negative connected to your power source from your battery. So your battery usually goes directly to these rails, and then you pull power off of the rails and connect it to another port like this. All right, so maybe 3 and 4, you run positive, negative, and then you can plug in LEDs and so on and so forth. Okay, that's how a breadboard works. All right, so what's a series circuit? A series circuit is when you have multiple things that are using the electricity and they are in tandem. So they used to make Christmas lights back in the day where it was a bunch of tiny little lights, but they were all connected in a row. And if there were, I don't know, 100 lights on the string and one burns out, okay, if the circuit is broken anywhere, if one of the lights goes out, then all of them go out. That's how they used to make Christmas lights. They don't do that anymore. We're going to go however they do it now. So the components share the total voltage when they are in series. So basically, you have things connected. If there's any break, the switch would turn off all the lights. So, for example, if you have a bunch of lights in a room and they're all running on a switch, then they're probably all in series because you turn one on, you turn them all on. They can be in parallel as well. It just depends. Actually, your lights in your room are not in series. They're definitely in parallel because if one burns out, they don't all burn out. We stopped wiring in series a long time ago for most things. However, you can use wiring in series to protect certain circuits in your home, stuff like that. Okay. To calculate the current, you sum all the resistance and use Ohm's law. So if you know the resistance, because like a lamp or some sort of object provides resistance in the circuit. So this lamp is providing resistance, this lamp is providing resistance. To figure out the current, you add up the resistance from lamp A, the resistance from lamp B, and then that's your total resistance that you use in Ohm's law to calculate the rate at which electricity is flowing. If this is 1.5 volts or whatever. So a series circuit, they are connected like this. So let's go ahead and make a series circuit in Tinkercad. We're going to create a new one with a breadboard, a 4.5 volt battery pack, 1 resistor, and 2 LEDs. Okay, so, and a switch. Let's go ahead and throw a switch in there as well. All right, so here we go. Back to Tinkercad. I'm going to stop my simulation. Where are my, oh, click this little arrow over here. I am going to grab a breadboard, click. Oh, that thing is huge. Oh well, that's the one we've got. Go right here. We're going to do this with the breadboard. All right, I'm going to delete these wires. We're going to kind of do this a little differently than we did. All right, so I'm going to have this battery pack here. Positive. Actually, it makes more sense for the breadboard to be on the right so we don't have to cross wires here. There we go. I'm going to have the positive end of my circuit come up this direction and turn right 90 to connect there, and black connecting to my power rails. It doesn't matter which side you connect to. I have just completely charged both of these on my breadboard, and what that allows me to do is it allows me to pull power. Well, you know what? So you can pull power from here if you want. That's fine. We'll just go ahead and do it this way. I'm going to bring my LED down. It's a series with 4.5 volts. And we have to have one path for our power. Okay? So I'm going to go ahead and make a copy. So if you do Control-C, Control-V, or you can grab another LED. And why don't we change this LED to blue or something? So you got a red and a blue LED. Now what happens if I run my positive to this side, okay, up through the LED and then back to negative? And let's go ahead and start simulation. My light bulb breaks. I have too much current. I have no resistance in the current, right? So to create a series circuit here, I want to come up through this LED, and I want to go into this path of this LED. So I'm going to come through out the positive, okay, bridge over to this port, up through these ports, connect. It's going to go up through the LED. It's going to come down. I'm going to bridge over to here. Now the electricity is going up through the LED. It bridges over from row 7 to row 5. It's going to go up through the LED, and we're going to come back to negative. Now notice when I start the simulation now, they didn't break. Because remember the rule that I just taught you with series circuits? You are kind of sharing the voltage, so to speak. So it kind of divides it up, and it's not, since these are providing resistance, it's not necessarily as dangerous for them, but they are. It says that it's operating at 38.8 milliamps. Well, we need to do something about that. So rather than use a wire right here, I'm going to go ahead and drag in a resistor. Uh-oh. I don't know what I just do. Okay, I'm going to grab a resistor. I'm going to drag that into the system, and I'm going to connect it right here. Okay, start simulation. They're barely on at all, hardly at all, and that's because I have too much resistance. So let's chalk that down. We probably don't need 300. Let's try 100 ohms and see what happens. Start simulation. Looks like they're operating pretty well. Okay, so brown, black, brown is what's working for us. Now I also said we need to drag in a switch. So I'm going to pick a spot to put a switch. It doesn't matter where you put it. You can put it with the resistor side or the positive side. I'm going to put it on the positive side just for kicks and giggles. Grab a switch. Okay, bring that in. I want it connected to the positive side, so I'm actually going to rotate this upside down, drag it to here. You typically, with these switches, supply the power to the center pin and then use one of the other ones to travel. So I'm going to come through here, around and down to the center pin, and then up and over to the red side here. Okay, let's go ahead and start. Lights are on. Flip the switch, lights are off. We've got a series circuit with 4.5 volts. Okay. Awesome. Fantastico. What a beauty. What an absolute beauty. All right, let's go back to our lesson. So we just did a series circuit with, we did not use a well, we did use a breadboard. It's not listed. That's okay. I'm going to go ahead and add that for the sake of the lesson. One breadboard. All right, and then the next kind, which we're not going to do one of these, so I'm going to let you try and figure it out on your own. A parallel circuit, multiple paths for electricity. So with this one, you only have one path for electricity to go. It's through both of those bulbs. Every single electron is traveling through both of those bulbs. Well, in this case, that doesn't happen. One electron can kind of ends up kind of choosing which path it wants to go. So the difference between a parallel circuit and a series circuit is before they kind of shared the voltage. And here, each of them receives the same voltage as the battery. Okay, so each of them is receiving the same voltage that the battery is providing. If one of the branches breaks, the other two will continue to work. So if this bulb goes out, electricity can still flow down the other two paths. So that's the big difference between a parallel circuit and a series circuit. So these aren't necessarily exactly the same, but that is the difference. So electricity can flow out, can travel through. This is getting, if this is 1.5 volts, this is getting 1.5 volts, this is getting 1.5 volts, this is getting 1.5 volts. All right, fantastic. Here's some warnings before you do your lesson. I don't want to see any of this on your circuitry. At no point should one node have two wires connected to it. If you do that on your circuit, that part of the circuit is going to be marked down. Okay, don't do that, because people just start hooking stuff up and then they don't actually understand what kind of circuit it is. So I want everything to be highly controlled. Try and make your wires nice and neat. Easy for us to understand. Everything is connected to one port. We can see the flow of electricity. That's the goal. So no 2 wires in one port. Although the program allows it, it is not really a possibility when you're actually dealing with a real breadboard. And although you could solder or something like this, I don't want you guys to do that. I want you to segment everything out so you don't have 6 things hooked up to each other at once. Okay. Your assignment is listed on the website. I really appreciate you guys tuning in. Hopefully this has been a helpful video for you. Hopefully you learned something. And when you are submitting your work, you're going to be taking screenshots of Tinkercad on a Macintosh that is Command Shift 3 or 4. 4 allows you to choose a section of the window, and 3 allows you to just takes a screenshot of the whole screen. What else? If you're on a PC, you're going to use the print screen option, which is in the top right hand corner of your computer, and then open up Microsoft Paint and paste it in. So you use press print screen, open up Microsoft Paint, press Control V or paste. It'll paste the image, and then you can crop it down. When you submit your pictures, please make sure they are the correct size and you don't have like it zoomed way out. So I need to be able to see the resistor that you're using. I need to be able to see where things are plugged in and how things are joined. Another thing that might be helpful is like if you want to keep track, you can actually color your wires here, so you know that this is kind of the positive side of the circuit, and this is the negative side. You can do that if you so choose. Okay, that's it for this video. Thanks for watching, guys. It's been a lot of fun, and I hope you learned something. Please show up to class and ask lots of questions. So please watch this video before you come to class so you can ask questions. Okay, we'll see you later.